All right, today I'll talk about some of the 3D rate of transfer modeling work we've been doing on blue waters, and here in particular this is 3D rate of transfer in the atmosphere with a focus on transfer through clouds. I'd first like to acknowledge members of my group who have contributed to this talk, Brian Jewett, Bill Chapman, Ali Jones, and David Jackson, as well as my sponsors and other people who have helped out down below. Okay, so I think everyone in this room is familiar with why we need accurate predictions of weather and climate. It has this massive societal impact, of course, from the everyday on how we dress, to even the talk we heard today by Charlie dealing with city planning, to commerce and public warnings. Just as an example here, we could take a look at some of the uncertainties that we have in our ability to predict weather and climate. And what we find out is that we're often far from where we need to be. So taking a look here at just this little clip from a TV station where we could see a few days before Hurricane Sandy, we're looking at different model projections of hurricane tracks. And you can see it's making landfall at different times anywhere between North Carolina and Maine. And those types of uncertainties are ridiculously large for such an important event. We could translate that also in looking at climate projections, that the uncertainties are also much too large. So Don talked about this particular slide this morning. It was hot in the news last week when the U.S. National Climate Assessment Report came out, showing on a global average here what the surface temperature projections will be in about 100 years from now. And in the business as usual scenario, we have about an 8-degree warming, but what I want you to focus on is the 5-degree spread in model projections. Again, that is a massive range for our current estimate of the uncertainty. And of course, when we sit back and say, well, why are the uncertainties so large? The usual suspects come up. So for example, inadequate resolution. Of course, we're always trying to push towards higher spatial and temporal resolutions in order to resolve smaller scale phenomena. But also, I'd like to point out the poor representation of physical processes that we put into these models. In an effort to make the simulations run fast enough in order to produce predictions that make it out in time before the event has actually happened. Okay, and these include turbulent processes, land-atmosphere interactions, cloud and radiation processes. Now, greater computational resources have often been targeted to achieve higher resolution. Okay, we heard that this morning as well, also in Don's talk. And in my community, we often actually spend much less time, unfortunately, trying to deal with the inadequate treatment of the physical processes that go into these models. Another thing with the modeling aspect is that the parameterizations to describe subgrid scale processes that are based on observations are often plagued by inadequate observations to begin with. So we have a global satellite network that retrieves, here my interest is in clouds, we retrieve cloud properties all over the world, and when we take a look at the uncertainty characteristics of those data sets, we find order of magnitude type errors that are just not good enough. Right? They're terrible, and they're terrible for reasons I'll describe here in a minute. When you come back, when we look at these model spreads in climate projection, for example, much of this spread, if you pick up the IPCC report, you'll find statements like, the treatment of clouds and radiation processes have been identified as the largest contributor to model prediction error or model prediction spread. But this is also true in the remote sensing of cloud properties from satellite, that the treatment of radiation is extremely poor. So I'm going to focus on radiation, and I'll make the statement here that when we take a look at these weather and climate models, in fact, all environmental prediction models, whether we're dealing with cloud resolving model, numerical weather prediction models, climate models, and pretty well all remote sensing algorithms that use passive measurements of scattered sunlight or terrestrial radiation. These all make the same assumption when doing the radiative transfer, and that is the radiative transfer is reduced down to one dimensions. In other words, or sometimes called plane parallel, where the media is assumed to be horizontally homogeneous out to infinity, such that the radiative transfer only varies in the vertical direction. Because I had dinner with him. There's anyway. Right. So this assumption is made in our environmental prediction models. The reason why we make this assumption is that it's computationally fast. And when it comes to the remote sensing problem, which also uses 1D radiative transfer assumption, it makes the inverse problem tangible. Okay, and I'll point out that we know how to do 3D radiative transfer in the atmosphere. The issue is that it's just too computationally expensive for our modeling capabilities, and that for our remote sensing, we actually have no good inverse solution in the face of 3D radiative transfer when deriving cloud microphysical and optical properties. Okay, so just as a showcase, this is what a 1D or a plane parallel cloud looks like from space. Okay, I've never seen one like it. Okay, and I've looked hard. What we tend to find are clouds that look more like this. They're very. This is over a 10-kilometer domain at 15 meter resolution from the Esther instrument. Clouds are very structured, lots of texture. If you look closely, they cast shadows upon each other. Okay, we have net radiative flux divergence coming out of the sides of the clouds. These things are not present in these types of clouds. Okay, but there's been debate because we were running our models and because we are spending billions of dollars on building satellites to retrieve geophysical information about clouds and aerosols and radiation. We needed to be sure that the 1D assumption was good enough. Testing that has been very, very difficult over the decades because it's a computationally challenging problem. So what has emerged in the 1970s, 80s, and 90s were excuses on why 1D is good. Right? We need to come back to our program managers and tell them, it's good enough. We're doing okay. These predictions are fine. But that didn't. But as the data became more available, and our modeling capabilities became better, and because of our computational resources, we came to realize that this issue with the plane parallel assumption is quite serious. In order to demonstrate the magnitude of how bad this assumption is, we had to turn to satellite observations. And here I'm just going to show you a quick result from the MISR instrument. MISR's been up there for 12 years. It measures the angular distribution of scattered sunlight. Okay, and we've merged it with some MODIS data, which I won't describe here, but let me just show you this particular figure. Here we ask from the data, what is the fraction of the observations that we have where the angular distribution of the scattered sunlight is within 5% of our plane parallel expectation. Now, MISR is in a sun-synchronous orbit, so the equator crossing time is set to about more or less 10:30 a.m. So we have the solar zenith angles that are sampled here, and we're looking at a January and a July. And I guess the way to look at this for easy digestion is that the red areas will represent regions that are frequently where the plane parallel assumption seems to be, let's say, good enough, and the blue regions are not. And basically what we find is that in regions that are dominated by stratiform clouds, and when the sun is at a high elevation, we find that, yes, frequently these clouds do pass for plane parallel. But you see there's a lot of blue in these maps, and indicating that in really about 3/4 of the planet, this is a terrible assumption. And when we actually take a look at why, for example, if we just connect to the average texture of the clouds, which would be a measure of the heterogeneity, if you will, of the cloud scene, what we find here, the red would represent smooth textured clouds, the blues rough textured clouds, and we see there's a strong connection between the angular deviation from plane parallel and the texture of the clouds, which is what we'd expect. So given that this is a global problem, we have to deal with it. So we're coming back to some very basic questions, and that is, what are the radiative heating rates for real clouds and their impact on the dynamics? Okay. What we're using Blue Waters for is we're trying to produce the first simulation where we do proper 3D radiative transfer heating rates connected to the dynamics at the same time steps as the dynamics. Okay, and this will be a first. How do we, of course, it's computationally challenging. How are we going to overcome these computational challenges? And then from the remote sensing side, how do we solve these remote sensing problems in the face for retrieving cloud and aerosol properties in the face of 3D radiative transfer? So our starting point is to build a 3D radiative transfer model for the atmosphere for Blue Waters. And we decided to hone in on a Monte Carlo technique for obvious reasons with Blue Waters. And we decided to work with a open source code that was introduced by some NASA DOE funding way back. Is that my timer?
No, I'm sorry.
Okay, sorry. Right, it's a Monte Carlo radiative transfer model, dubbed I3RC for, I forgot what it stands for now. Intercomparison of 3D radiation codes, that's it. It's an international effort that was done back in 2005, where about 20 or so models from around the world got together to compare their 3D radiative transfer solutions. The issue at the time being, well, we have no 3D benchmarks. The only way to look at how well our models are doing is to compare them with other models. And in that light, what we're dealing with here is a model that has a solar source only. It has lots of nice tools built into it to create these atmospheric domains. And during this consensus benchmarking phase that was done, the model spreads were shockingly large. The Monte Carlo noise was much smaller than this 3.5% that they are reporting here in terms of model spreads for particular solutions. So we've taken that code and we've done our own benchmarking work with it, where we've also derived some analytical solutions. And we've run it to really low noise levels and compared it to some of our benchmarks that are based on analytical solutions, as well as reciprocity tests, which have been very useful in many ways. And what we found was we were able to debug some of this open source codes that's out there, getting ourselves down to really high accuracies with respect to our analytical benchmarks. We also went ahead and we added terrestrial radiation as a source. We added heterogeneous surface reflectance and emission. We were able to track the order of scattering now, and we're able to end these simulations once we achieve a particular accuracy that we're interested in, and so on. And we're currently in the process of doing adding broadband integration so we can calculate heating rates. Our goal is to couple this with the weather research and forecasting model, which is already on Blue Waters that we've been running. We've run a wide range of simulations, everything from small trade wind cumulus clouds to tornado outbreaks that I think you'll be talking about later on, right? So I'll let him talk more about that scene. And then what we do here, we create basically these synthetic satellite images where we run the radiative transfer through the atmosphere using WRF as our input to to our domain file. So we have this conversion between the single scattering properties of the atmosphere, which we could extract from WARF, that we ingest into our radiative transfer simulations. So, you know, and here's one example. I believe this is the largest 3D radiative transfer simulations ever done for the atmosphere. I only checked a little bit yesterday, and I found out that the last biggest one was one I did back in 1998, which I remember took me 3-4 months to get done on a small cluster, and it was a quarter of this size. Anyhow, this is the simulation, and if you stare at a lot of satellite images like I do, it looked real. The one beside it is actually a satellite image of the tornado outbreak. We chose a time step here in the simulations before the anvil stage took place, because it was just going to add to the compute time, and we didn't want that. Anyhow, while our goal is to get our long-term goal is to answer these questions with regard to heating rates on cloud dynamics and atmospheric dynamics. Our short-term application, that's going to take years to work out. Our short-term application has been to deal with numerous remote sensing problems. And I thought for this audience I'd come up with this particular problem that I have a master's student working on. So from that MISR instrument that I showed you, we derived stereoscopic cloud top heights. And hot in the news about a year ago was that the analysis of this data by Roger Davies, who's turned out my PhD advisor, showed that from the data that the cloud top heights tend to be dropping with time at a rate about 45 meters per decade. Not a lot, but still, when you take a look at the equilibrium surface temperature response to a cloud top height change that's much, you get about a 0.35 Kelvin change. And if you compare that to the CO2 response from the observations over the past 12 years, it's about 0.09 kelvins. Okay. No feedback has been included in these. This is just a radiative convective equilibrium calculation. So the implication here, there's a strong climate implication here of negative feedback to the climate system from these dropping heights due to radiative cooling to space, and the news media was full of the sky is falling type thing. And NASA program managers have dubbed this as one of the top 10 finds in the last decade from their Earth observing system. So the thing with MISR, it produces these stereoscopic heights, and the question is, when you're dealing with these stereoscopic heights, you're looking somewhere deeper into the cloud. You're not necessarily looking directly at cloud top. And what we don't understand is the air characteristic of stereo heights in these semi-transparent media. I think it's a robotic vision issue as well, but it's certainly an issue with MISR. So we wanted to study I had Dave and one of my master's students study what the air characteristics are for stereo retrieval for a media like clouds. And of course the answer will depend on the 3D distribution of cloud properties, the sun view geometry, the resolution, the wavelength, etc. And here's some of his early results. It's incomplete. Here we're taking a look at, for some stratiform clouds, the air is a function of the optical depth of the clouds. And of course what you find is that the juicier the cloud, the smaller the air, which kind of makes sense to us. And the air is here being on the order of 10 to 20 meters. And it also depends on the texture of the cloud. So as we go from more stratiform to more cumuliform clouds, the airs increase substantially, from going from one case to tens of meters all the way up to hundreds of meters. So when we start talking about these 45 meter per decade changes in cloud top height from the observations, we have to ask ourselves, well, maybe it's not the cloud top heights that are changing, but something about the texture of the optical thicknesses that are changing, not just the cloud top heights. From the climate modeling perspective, who use satellite observations to help benchmark their simulations, we need to be careful in using results such as the ones I just showed you for benchmarking the climate models and tuning the climate models, as there still may be problems with the observations. All right, so I'm just returning back here to these questions that we're going to be tackling, and these are questions that will take decades to fully address. But we hope, in terms of the heating rate, getting the WRF model and the 3D rate of transfer model coupled, we hope to have some first results in about in less than a year. Thank you.